Let us begin. We're going to be working problem 66 on page 83 in section 3.2. We're asked to find the displacement of a plane that experiences a uniform acceleration. By uniform, we mean constant, or it's unchanging, right? Uniform, it means the same. So we have a uniform acceleration from one velocity to another velocity, from 66 meters per second to 88 meters per second in a period of 12 seconds. Now, a problem includes direction for us. We see that it goes from 66 meters per second to the north. So I'll put an N above that. And 88 meters per second still to the north, so still in the same direction. We could say that at one point in time the velocity vector is pointed this way with a magnitude of 66 meters per second, as long as this way is north. We say this is north. And at the next moment, we see that the velocity vector is now longer, has a greater magnitude, now of 88 meters per second, but still pointed towards the north. This velocity vector, we'll call this one our initial velocity vector, right? Because that's the velocity we start at. This velocity vector, we'll call that our final velocity vector, because that's the velocity we end at. We could represent the change in this velocity both visually through the vectors and numerically. We would say the change in velocity is Vf minus Vi, or the final velocity minus the initial velocity, which is a final velocity of 88 meters per second to the north in the positive direction. We'll define that as the positive direction, minus 66 meters per second, also to the north, so still positive, which gives us a change in velocity of 22 meters per second. We see that change in velocity would be represented visually if we were to subtract these two vectors from one another. Right, here's our numerical subtraction, but we could also have the change in velocity as a vector sum, or vector difference, which would be our final velocity vector minus our initial velocity vector. Here's our final and initial velocity vectors. We could rewrite this difference, mathematical difference, as the final velocity vector plus the negative of our initial velocity vector. Mathematically, these two are equivalent. We know how to add two vectors. I take the tail of one vector and place it at the tip of the other. So now I'm going to move these two and start by taking, I take the final velocity vector. I'll represent that here again with my velocity vector pointing towards the north. That's my final velocity vector. In order to add the negative of the initial velocity vector, that means by the negative I mean I change the direction. Originally he's headed towards the north, now I got to move him towards the south, or the negative direction. So this initial velocity vector is now placed with the opposite orientation, so pointing to the left, or to south, or to negative, all the same. I need to place the tail of this velocity vector, which is now pointing south, at the head, or the tip, of the first vector, right, of my final velocity vector. And now he's pointing back the opposite way, right? So now, because of this negative sign, this initial velocity vector was pointing towards the north. Now it's pointing towards the south. See how this velocity vector, these two are being added to each other. We know they're being added because now we have head to tail, or the arrow to the tail. All that's left is this little vector here, our resultant vector. We'll represent him with an R. That's still pointing to the right. Okay? This resultant vector also happens to be our acceleration vector. Right? This is our acceleration vector for our change in velocity. Right? As long as we look at this over what period of time in which it happened. Here we have the mathematical difference between our two velocities of 22 meters per second. If we wanted to find the mathematical value of our acceleration, we would take the average acceleration and know that that's defined by the change in velocity over change in time. The change in velocity we already have as 22 meters per second. What period of time did this change in velocity occur? Our problem tells us it happened in a period of 12 seconds. So divided by 12 seconds. So we get 12 meters per second, 22 meters per second rather, divided by 12 seconds gives us 1.83 meters per second squared as our average acceleration over that 12-second period of time. If we took this velocity vector and divided it by 12, which then would make the magnitude smaller, then we'd see, but still pointed the same direction, we'd still see a positive acceleration. So our object, our airplane, is accelerating in the positive direction. That makes sense because our speed was changing from our velocity from 66 positively to 88. All right, all that to say, what we're asked to find is what was our displacement. What was our displacement? By that we mean some change in x. That's what we mean by displacement, and that we don't know. What we do know is that our initial velocity was 66 meters per second, specifically positive or to the north. We know our final velocity was in the positive direction at 88 meters per second. We know the time in which this occurred. This occurred over a period of 12 seconds. We want to find what was the displacement. I need a kinematics equation that relates initial velocity, final velocity, time, and displacement. I actually don't have one of our three equations. One of our three equations does not immediately give us a relationship between these four variables. Instead, we have to follow a two-step process here. The first could be we could calculate what our another variable, like acceleration, which we did. We did find what the average acceleration is. So we can write that out. So we also know this. We could have found this following using a kinematics equation that relates these three, initial velocity, final velocity, and a change in time, to acceleration. These four variables are related to each other in this kinematics equation. So we could have solved and found this acceleration, which really we did, just in an indirect way, find this average acceleration through this formula. Now that we have acceleration, time, final velocity, and initial velocity, we just need some equation that relates three of these knowns to the one unknown of change in position or displacement. We do have such an equation. We know that if I can find the change in position or displacement, if I know the initial velocity times the change in time that occurs, plus 1/2 the average acceleration times the change in time in which that acceleration occurred. I know time, I know initial velocity, and I know acceleration. So I can find displacement. I plug in my values for each of these. 12 seconds, 1/2 my acceleration of 1.8 meters per second squared, my time of 12 seconds squared. I see that 66 times 12 is 792 meters. Notice the seconds here cancel. I know 12 squared is 144 times 1.8 times 1/2. This whole quantity is 129.6 meters. I'll add this to my 792, and I'll see that I get 921.6 meters. That's the total displacement. However, I need to make sure I have the proper number of significant figures. Each of these has 2, so I'm going to round this just to 2 significant figures. So I'm just going to say 920 meters is my total displacement. 920 meters is my displacement. There's another way visually I could see what's happening here, and that is through a graph. So I'm going to quickly set up a velocity time graph in which we know the area under the curve of a velocity a velocity curve on a velocity time graph. The area under the curve is our displacement velocity in meters per second. I'm just going to draw out a general graph of what this looks like. We know that our velocity started at 66 meters per second. I'll say that's something like here. Say this is something like 66. And went up to 88. I'll say this is something like 88. We did that over a period of 12 seconds. We'll say this is 0 seconds, of course, and this is 12 seconds. So we started from 66, ended up at 88 after 12 seconds. I'll connect these two lines here. The area of the curve we're talking about that corresponds to displacement is this whole area inside these two shapes. First is our triangle up top, and the second is our rectangle down below. So if I found the area of my triangle, and I added that to the area of my rectangle, I'd find together those give me the displacement. I would find that geometric value of the area of this triangle and this square, this rectangle rather, gives me 920 meters. Notice here, this is our change in velocity. This is our change in time. So the height of this triangle is change in velocity from 66 to 88. The base of our triangle is change in time from 0 to 12 seconds. The height of, and then 1/2 of that gives us the area. That whole quantity, this whole geometric area, is contained within this term of our equation. 1/2 acceleration times time. This should time squared. This initial velocity from 0 up to 66, that represents that whole distance here, represents our initial velocity. We still have the change in time as the width of or the length of our rectangle. So the length of our rectangle as change in time, the height of our rectangle as initial velocity. So this whole rectangle, the area of that rectangle, corresponds to this term here. So this is how visually we could see the displacement of our airplane as it goes from 66 meters per second to 88 meters per second. All right, thank you.